Today we are going to take a look at three more methods for apportionment. We have Jefferson's method, Adams' method, and Webster's method. They are all very similar except for one small little change, which is why I've chosen to do them all at once. The first method we're going to look at is Jefferson's method, which was developed by Thomas Jefferson. I mentioned in the last video that initially Hamilton's method was voted on, but George Washington vetoed it. After George Washington vetoed Hamilton's method, Jefferson's method was chosen as the method for apportionment, and it was used from 1791 to 1840. It is still used in many countries, such as Austria, Brazil, Finland, Germany, and the Netherlands. One aspect of Jefferson's method that made it seem more fair than Hamilton's method is that there are not the extra seats to be given out after the initial apportionment. So, here are the steps for Jefferson's method. First, you calculate the standard divisor, just like we did with Hamilton's method. To do that, you take the total population and divide by the number of seats. Then, you find the standard quota for each state. To do that, you take the state population and divide by the standard divisor. So far, nothing is different than Hamilton's method. Now, here's the part that makes Jefferson's method a little bit different. Instead of using the standard divisor, we are going to find a modified divisor so that when each state's modified quota is rounded down, the total is the exact number of seats that we need to apportion. In this particular method, the modified divisor is always going to be slightly smaller than the standard divisor. Then, each state is given its modified lower quota. Let's look at an example. So, we have a small republic consisting of 6 states, and it has 250 seats in its Congress. We want to find the apportionment of the republic under Jefferson's method. So here we have 6 states, A through F, and I've given you the population of each state. I will tell you that everything we do today is going to be a lot easier if you use spreadsheets, because there is a little bit of guess and check. So I'm going to flip over to my spreadsheet. Right now, all I have is the exact same information that was on the slide. The states, the population, and I know that total we have 250 seats in Congress. So, first thing we need to do is find the total population, which means I add up the state populations. You can do that by hand, or you can have the spreadsheet do it for you. To do that, if you type equals sum, parenthesis, and highlight the cells that you want to add up, then hit enter, it'll calculate the total population of this republic, which is 12,500,000. So I'm going to go ahead and write that down. Next, I need to find my standard divisor. To do that, I need to take the total population and divide by the total number of seats. Again, you can do that on a calculator, or you can have the spreadsheet do it for you. I'm going to type equals, highlight the population, divided by, highlight the total number of seats, hit enter. So my standard divisor is going to be 50,000. So I'm going to write that here. Now, I need to find my standard quota. To do that, I need to divide each state's population by my divisor. The shortcut to do that in a spreadsheet is to say equals this divided by this. Enter. Now, you can either keep going through for each row, or you can try to copy and paste. But if you just copy and paste, you're going to get an error. Since we always want to divide by 50,000, I can change this by putting dollar signs in front of the B and in front of the 10. That's going to tell the computer that I always want to divide by B10. So now, if I copy and paste, I'm always dividing by B10. And that gives me my standard quota for each of the states. Now I'm going to go ahead and write that on the slide. Now that I've got that written down, Jefferson's method always uses the lower quota. So I'm going to go ahead and round each of these values down and see how many seats I've apportioned. Again, we can do this in our spreadsheet. So in the next column, I have labeled this lower quota. So I want to round down all of the standard quotas. So if I type equals floor parenthesis and click on my standard quota and hit enter, it will round all of these numbers down. And I can copy and paste that. Now, I want to add these up and see how many seats that is. So I'm going to type equals sum and add up these cells. I have only apportioned 246 seats, but I'm supposed to have 250. So I'm going to write this down on my slide and we'll come back. So far, everything we've done is the same as Hamilton's method. So here's where it gets a bit tricky and where the spreadsheets definitely help. Jefferson's method says we are going to change our divisor. It says that the modified divisor will always be less than the standard divisor. So I'm going to choose a number that's a little bit lower. I'm going to say 49,000. And when I hit enter, it's going to do all of the math for me. And the number that I really need to pay attention to is this one. I need to give out exactly 250 seats. Right now I've given out too many. So clearly I made my divisor too low. So I'm going to go a little bit higher. 49,500, and that does give me 250 seats. Now, there are multiple numbers that will get you to the right number of seats. For example, if I made my divisor 49,501, it's still the same number of seats. So, my modified divisor is going to be 49,500, and then I'm going to copy my modified quotas and my apportionment based on the Jefferson method. So here's my final apportionment based on the Jefferson method. I just copied down what was in the last column on my spreadsheet. Remember that the goal is to have this total here be however many seats you started with, which in this case is 250. Now, couple issues with the Jefferson method. First of all, it violates the quota rule. If you look here, state B ends up with an apportionment that is larger than its upper quota. So if we go back to the beginning, The lower quota is 138, the upper quota would be 139. The quota rule that we talked about in the last video says that each state should either get their upper or lower quota. State B got more than their upper quota. Well, that's because the Jefferson method favors large states. In 1791, Virginia was the largest state. Jefferson was from Virginia. It made sense that he would want to come up with a mathematical model that favored his home state. Jefferson's method was used until 1840. In the 1832 apportionment, New York was given 40 seats in the House of Representatives when its standard quota was only 38.59. This was the first time that the Jefferson method had produced a violation of the quota rule, and Congress was in an uproar. Because of that, this is the last time that Jefferson's method was used for apportionment. After the 1840 census, a different method was used. Let's continue with the next method. Our next method is the Adams method. It was developed by John Quincy Adams. After serving as president, he was then a congressman for the state of Massachusetts. After this debacle with New York in the 1832 apportionment, he proposed his method, although it was never used for apportionment in the U.S. House of Representatives. His method is very similar to Jefferson's method. You start by finding the standard divisor, find the standard quota, but here's the difference. You want to find a modified divider so that when each state's modified quota is rounded up, the total is the exact number of seats to be apportioned. So instead of using the lower quota like Jefferson's method, we're going to use the upper quota. So let's look at the same scenario. We have this same small republic, 6 states, 250 seats in Congress. I've copied stuff from the previous example that's the same. The total population is still the same, the standard divisor is still the same, the standard quotas are still the same. So let's go to our spreadsheet. I made a new tab for Adams method. I'm going to go ahead and start off the same way that I did for Jefferson. I need the total population, even though it's the same problem and I've already copied it onto our slide. I need to know the standard divisor. And I need to know the standard quota. All of this is exactly what we did for Jefferson's method. Here's the different part. I'm going to use the upper quota instead of the lower quota. To get the upper quota, we use equals ceiling. Floor means round down, ceiling means round up. So I'm going to round up all of my standard quotas. Just like I did on the previous page, I'm going to add up all of those upper quotas. And I need this total to be 250. So I copied my information to my slide. Now I'm going to go back and modify the quota. For the Adams method, your modified divisor is going to be a little bit larger than your standard divisor. So I'm going to take this number and increase it a little bit. So let me try 51,000. Okay, that was too much. So let me go with 50,500. Okay, let me try 50,700. Now my total is 250. So that's my apportionment for the Adams method. So I'm going to go ahead and copy my modified quotas and my final apportionment for the Adams method. So I took this information and copied it here. My modified divisor was 50,700. I have all of my modified quotas, and then rounded all of those up to get my final apportionment. But there are some issues with Adams method. If you look here, again, state B. The standard quota for state B was 138.72. So state B should either get 138 or 139 seats. It gets 137, which is lower than its lower quota. So Adams method can violate the quota rule, but it will give a state less than its lower quota. And that's because the Adams method favors small states. So here, the largest state got fewer seats than it should have. Now, at the time that this method was proposed, Adams was a congressman from Massachusetts. At the time, Massachusetts was actually a medium-sized state, but I'm guessing he was sick of his state losing seats based on the Jefferson method to some of the larger states. So his method favors small states. Unfortunately for him, it was never actually implemented. The last method we're going to look at is Webster's method. This was developed by Daniel Webster, who again was a congressman from Massachusetts. He proposed it in 1832, but it was not accepted. It was, however, used in 1842 and in the early 1900s. Weirdly enough, although Congress officially used Hamilton's method between 1850 and 1900, they purposely chose the size of the House of Representatives so that Webster's method and Hamilton's method produced the exact same apportionment in 1852, 1872, and 1882. Many people consider Webster's method to be one of the most fair methods of apportionment, so it's interesting that it was only used for such a brief period of time in the United States. Webster's method starts off exactly the same as Jefferson and Adams' methods. You find the standard divisor, find the standard quota. But Webster's method, instead of always rounding down or always rounding up, rounds normally. So, in this method, we need to find a modified divisor so that when each state's modified quota is rounded the standard way, the total is the exact number of seats to be apportioned. We might have to make our modified divisor larger if we're apportioning too many seats, or make it smaller if we're apportioning too few seats. And then whatever the modified rounded quota is, that's the apportionment for each state. Let's take a look at this same example again. We have the same small republic, 6 states, 250 seats in Congress. Again, I've copied all of the things that are still the exact same as when we did the Jefferson and Adams methods. I'm going to go to my spreadsheet. Here, I have already input all of the information that is the same from the previous two methods. Populations, total population, number of seats, standard divisor, standard quotas. Now, I need to have my spreadsheet round my quotas. To do that, all I type is equals, round, parenthesis, and click on my standard quota. Then I can copy that for each of the rows. And I want to add up the rounded quotas. So equals, sum, parenthesis. Right now, I am giving out 251 seats, but I only have 250. I'm going to go ahead and write this down on my slide, and then we'll come back and modify the divisor. So, all I did was round the standard quotas the normal way, where if the number or the digit after the decimal point is 5 or higher, you round up. If it's 4 or lower, you round down. So, since I have given out too many seats, I need to make my divisor larger. So I'm going to try 51,000. No, that's too many. Maybe 50,500. Oops. No. Maybe 50,100. Okay, that works. Now my total is 250. So I'm going to copy these modified quotas and the rounded modified quotas onto my slide. So, using the modified divisor 50,100, I got these modified quotas, rounded them, I have a total of 250 seats, so I'm good. That's my Webster apportionment. Now, if you check the quota rule here, you'll see that we do not violate the quota rule in this situation. Mathematically, it is possible to violate the quota rule with the Webster method. You could violate the upper or lower quota, but it is very rare. In fact, if you go through historical data from all of the censuses from 1790 to 2000 and redo the apportionment with the Webster method, there are never any violations of the quota rule. So, let's summarize these. If we look at the 4 methods we've looked at so far, Hamilton, Jefferson, Adams, and Webster, Hamilton's method does not violate the quota rule. Every state either gets its upper or lower quota. But Jefferson, Adams, and Webster's methods could all violate the quota rule. There were 3 paradoxes that we looked at with Hamilton's method. The Alabama paradox, where you change the total number of seats in the House of Representatives, make it larger, but a state still loses a seat. Hamilton's method is the only one that is affected by that paradox. We have the population paradox, where a state's population increases, but they lose a seat to another state that did not have as big of an increase in their population. Again, Hamilton's method is the only method that falls victim to that paradox. And then we have the new states paradox, where a new state is added, they get their appropriate number of seats, but when you redo the calculations, there are some changes amongst other states. Again, Hamilton's method is the only method that is affected by this paradox. Hamilton's method and Jefferson's method both favor large states. Adams' method favors small states. Webster's method is fairly neutral. Last thing to talk about is the Belinsky-Young impossibility theorem. In 1980, Michael Belinsky and H. Peyton Young discovered that there are no perfect apportionment methods. Every apportionment method either violates the quota rule or falls victim to paradoxes. As you can see here, Hamilton's method does not violate the quota rule, but it does have several paradoxes. The other 3 methods don't have any known paradoxes, but violate the quota rule. So much like our voting methods, we will never have a completely fair apportionment method.